Hello, so this is OCR A-Level Chemistry, the paper H43201, paper 1, and this is the June 2017 question 21 on acids and buffers. Okay, so first thing we're going to do is read through the question, and it's telling us it's about the properties and reactions of ethanoic acid. It tells you it's a weak acid, so well worth noting that. It gives you the dissociation constant, and in a kind of reverse of the normal question here, where normally you're asked to figure out the pH, this time they give you the pH, and what they're asking for is the concentration of ethanoic acid. And so I've started off by writing that down here. Now before I jump in to putting the equation I'm going to use, I'm going to try and talk you through it here. These questions invariably come down to the one equation to rule them all. Ka equals H plus times A minus divided by HA. Now, this is a weak acid, so you know that the concentration of H plus is equal to that of the conjugate base. So those two are equal. So therefore, Ka can be simplified to be the concentration of H plus squared divided by the concentration of the weak acid. Now this is our weak acid here. We want to get this on its own, so we're going to multiply both sides by the concentration of weak acid. Ka times by Ha equals the concentration of H plus squared, and then we're going to divide both sides by Ka. So over here we have this. Now we're not given the concentration of H plus, but we are given the pH. So the concentration of H plus is 10 to the negative pH, so that's 10 to the negative 2.440, which equals 3.63 times 10 to the negative 3. Excuse me. So we're going to put that up in here. 3.63 times 10 to the negative 3. Remember to square it. And Ka is given to us 1.75 times 10 to the negative 5. Now you got 1 mark for working out this concentration of H plus. You get a second mark for writing this here, for having rearranged the equations and got to here. And you get the third mark, the final mark, for reading the full question. 3 significant figures, so this is 0.753. Onwards. Right, here ethanoic acid is added to another weak acid. And this weak acid, they give you the Ka. What you have to remember is that a larger Ka equals more dissociation. This is the equation. So it's more dissociated if it's got a larger Ka. Be really careful here, because although 2.19 you look at initially, see 1.75, and you might, in a rush in an exam, pick this one as being higher from just the 2.19. Make sure you pay attention to the powers. Now here it is pretty clear that we have this one being the stronger acid from both parts, but double check, they won't always do that. So I've already written in the bits that definitely won't change. Larger Ka, more dissociated, so the stronger acid. So this one is the one that is going to dissociate. So it is going to give you the conjugate base, and it's going to force the ethanoic acid to be protonated. So you just take your molecule and you add an H plus to it. I know it looks awkward, but it is the correct answer here. So that's your first mark. The second part is to label your conjugate acid base pairs. So we've just gone through all this and we've worked out that the fluoroethanoic acid is being an acid, so let's make it be an acid, and for easiness sake I would call it acid 1. Over here its conjugate base therefore has to be B and be B1 because the ones go together. You need to have an acid and a base on each side. Let's make sure it all makes sense. The ethanoic acid was being forced to be a base, it was being protonated, so that will be B2, and on this side here, that is acid 2. Okay, part C. The student plans to prepare a buffer solution that has a pH of 4.5. The buffer solution will contain ethanoic acid and sodium ethanoate. Okay, this is good. Your buffer has to have the weak acid and its conjugate base. So far, so good. The student's going to add 9.08 grams of sodium ethanoate to 250 cubic centimeters of 0.8 moles per decimeter cubed ethanoic acid. Okay, so there's no worry about them adding any of the sodium hydroxide this time. This is just a straight up working out the number of moles and then the concentrations of each of these two chemicals. The student assumes the volume does not change. That's relevant for part D. First thing, it's always coming back to this equation. However, this time, because it's a buffer, the concentration of H plus is not equal to the concentration of the conjugate base. So we're going to have to work both of them out. I've started it just to try and save you some time in the video. The concentration of the weak acid itself, ethanoic acid, it's just year 12 stuff, year 11 now, N equals CV. You're given the concentration and you're given the volume. Watch out for the units, but if you put those together, then you can get that it is 0.2 moles. Apologies there. Next thing, we've got to try and work out the amount of this. We've got a mass. Don't panic. N equals M over M. So that equals 9.08, which is given to us here, divided by 82.0, which equals 0.11073 moles. Now I'm going to stop at that point. So, the key thing here is this is all about the ratios. We've got the ratios of the moles, but the other way we could have done this is to get the ratios of the concentrations. So I would not have changed that concentration there, I would have left it as it was, but we'd have had to turn this into a concentration using concentration as number of moles over volume. Either of these is going to work here. We are asked to find the pH. To find the pH, you first of all need to find the concentration of H+. So we rearrange that equation. Concentration of H+ equals Ka times by the concentration of your weak acid divided by the concentration of its conjugate base. So this equals, from the previous question, 1.75 times 10 to the negative 5 times by, now here's where it doesn't matter that I've used the number of moles because the ratio is going to be the same. It's going to be 0.2 divided by 0.11073, or if you've rounded up already, 0.111, or if you just want to see, this would have stayed as a concentration there, 0.8, and we would simply have multiplied this by 4 because it was a quarter of a litre, and so what you would end up with is the same ratio between these two. It just depends how comfortable you are with the year 12 steps. Anyways, if you put all that through, you get to 3.16 times 10 to the negative 5 moles per decimeter cubed for the concentration. pH negative log to the base 10 of that H plus, which I'm going to assume that you can all press the buttons on a calculator and it should pop out at 4.50, and so that is us with the required pH. Part 2. When the student prepares the buffer solution, the volume increases slightly. Suggest whether the pH of the buffer solution will be the same, greater than, or less than your calculated value, and explain your reasoning. Now they've put your calculated value just so that it doesn't matter if you got the question wrong there. And the bit I tried to be talking about here was these ratios being the crucial thing. The second part of this is the ratio of HA to A minus will be the same. If you dilute this, you will dilute both concentrations by the same amount. And if that ratio stays the same, then it means that the pH is constant, or the same. Thank you very much.